Now that we know the basic components needed for the DC to DC power electronics, we can start with the first and simplest technology, which is the buck converter, also called the step-down converter. Its role is to decrease the DC voltage coming from the PV side to a most suitable one. In this video, we will show you its electrical circuit and the operation in continuous mode. After the theory, we shall present a simple example to better understand it. Here, the simplest version of a buck converter is depicted. Starting from the left, we have the power supply, for example, a PV generator, that applies the voltage at the input terminal of the converter. Then we have the switch control signal, for example, a transistor, and the resistive load RL, which receives the output voltage Vout. In this diagram, the voltage applied at the resistive load is plotted as function of the time. Hence, when the switch is on, the input voltage Vin is applied directly to the load, while when the switch is off, the voltage across the load is 0. This is the unfiltered output voltage waveform Vout of such a converter. If we calculate the average output voltage by integrating in time the voltage over one period of the signal, then the resulting average DC output is a fraction of Vin, where Ton over Ts is, by definition, the duty cycle that we already introduced. In general, the output voltage with such a high harmonic content is undesirable, and that's the reason why we include some low-pass filters. This is the topology of a more complex step-down converter. Once again, we have the switch here and the load, which is purely resistive. The filter elements implemented are an inductor L and a capacitor C. In this configuration, you can also see the flyback diode. Notice that in this case, the polarity of the PV module is the same as the load. Then both PV module and the load have the positive sides connected with the same branch. Let's start with the case when the switch is on. The current flows through the switch, the inductor, and then divides itself among the load and the capacitor branch. By applying the Kirchhoff law for a linear circuit, we can actually find out that the voltage across the inductor is given by voltage across the flyback diode, which is the same as the input voltage, minus the voltage across the capacitor, which in turn is equal to the output or load voltage. Now, in the previous video, we saw that the inductor works according to Lenz's law, for which the time derivative of current flowing through the coil is linked to the voltage across the inductor via the proportionality factor L, known as inductance of the coil. Moving from the derivative to the integral form of Lenz's law, the increase of current in the inductor in the on mode can be written as the difference of the input and output voltage divided by the inductance and multiplied by the duration of the on time. When the switch is off, the current flows only in this part of the circuit. Here, the energy that has been stored in the coil as a magnetic field will drive the current towards the resistive load with the help of the flyback diode. Now, with the Kirchhoff law during the off mode, we obtain the voltage across the inductor expressed as the difference between the voltage across the flyback diode and the voltage across the capacitor or the output voltage. In this case, we should also consider that the voltage across the diode requires a very small bias to start conducting the current, and most of the time this voltage is negligible as it is in the range of 0.7 volts or even less. Then the voltage across the coil is just the opposite of the voltage across the load. Once again, we can calculate the integral of the current through the coil and find out that the difference is negative, meaning that the current starts to decrease. Now, let's see how the voltages and currents develop during one cycle. When the switch is closed, that is during the on period, the voltage across the flyback diode is equal to the input voltage from the PV panel. Then, when the switch turns off, it reaches 0, creating a sort of squared wave. At the same time, the voltage across the inductor, the red line in the shown diagram, somehow follows the trend of Vd, but it is offset by Vout. So we have an average output voltage as the one depicted in the light blue. Then during the on cycle, the voltage across the inductor is V diode minus V output, while during the off cycle, it is just becoming minus V output. Now, about the current through the inductor, we have that during the on period it rises, and then as soon as the switch opens, it decreases. In a condition of steady state operation, also called the continuous mode, which develops after a certain amount of cycles, the flow of current across the inductor has to be zero. By simply substituting what we found in the previous slides, we obtain this equation. Once worked out, we find out that the output voltage can be written as the duty cycle times the input voltage. Remember that by definition, the duty cycle D can be anything between 0 and 1. So we can change the ratio between the voltages on the input and output sides of the DC-DC converter only by changing the duty cycle. Just an example to conclude the video, we have 12 volts at the PV side and we have to deliver 3 volts at the load side. This is the equation to use, and therefore we need a DC-DC conversion with a duty cycle of 0.25. So in this video, we learned how to create a DC-DC buck converter and, by varying the duty cycle, how we can tune the output voltage. In this case, always lower than the input voltage. In the next video, we will see how to increase this voltage with the step-up converter or boost converter.